G'day, I'm Dr. Kev, and as a doctor, I often have to fix people's problems. Just recently, an engineering student came to me saying that they had the need for moderately low speed, high yaw accelerations, and questionable reliability. And I said, you're in luck. I have exactly the formula for you, Formula SAE or Formula Student, depending on the continent in which you fail tech in. And the bonus is, it's also got the cure for today's vehicle obesity problem. Welcome to Car Design Workshop. Before we get going, I want to clear up that there's both Formula SAE, Formula Student, different variants of it. I happen to like Formula Student as a good descriptor. I think it explains the competition a little bit better in a title. But given that the competition was started in the US a long time ago, I'll give the respect and refer to it as Formula SAE from here on in. I've been involved with Formula SAE for most of my working life. In the year 2000, I helped start a team at the University of Western Australia. And since then, I've only had 2 years that I wasn't directly involved with the team, either as a student or a faculty advisor. And during those 2 years, I was working with workplaces that were full of Formula SAE alumni. So if we were to say that it takes 10,000 hours of deliberate practice to master a field, I can safely say I hit that mark a long time ago. I've stayed involved with Formula SAE for as long as I have because I think it's pretty important. It's great for the education of up-and-coming engineers, and I'm really glad to be a part of that education now, having benefited from it when I was a student. But I also really like the competition. And one of the things that I really love about the rules is something that's not in the rules, and that is a minimum weight. In most forms of motorsport, there are minimum weights required. So once you reach a certain weight, there's not a huge amount of motivation to make a car a lot lighter than that. I mean, you do get some advantages of being able to have ballast and move that about, but in Formula SAE, weight is always on your mind. And for good reason. Newton teaches us very clearly, if we want good performance from a car, we need to have high acceleration. There's only 2 ways to do that. Increase the forces from things like the engine and tires and so on, or decrease the mass. That makes mass or weight of the car a first order effect on performance. So in this video, I want to run through 7 things that I've learned from Formula SAE about how to make a car light. And the first of these is that you need to know where your weight is. Generally, if you want to improve anything, you need to have some way to measure it first. If we're looking to reduce the weight of a car, we want to see what's the low-hanging fruit. What are the areas that are easy to take weight out of? Where are the areas where we can save large amounts of mass on single items? Or where are the items where there's lots of them and we can save a small amount of mass in a lot of places? You may have noticed in previous videos for Project 171, I've been weighing just about everything. And that's become a bit of a habit following my time in FSAE. If a component is bought, you weigh it. If a component has different parts to it, you pull it apart and you weigh each part of it. Now, that's not going to mean that every single one of those components can be made lighter, but it helps to identify where there might be some chances to make some gains. If you're doing this as an iterative process, it's a really good idea to take a previous car and pull it apart. It gives you an idea of what areas have most of the mass, as well as where you're going to spend the bulk of your time. In terms of things like a Formula SAE team, weight saving is an iterative process. So it's not just iterative in a given car and the design and the manufacturing of that car, but also between cars. So knowing where you've been and where you might make changes is really, really important. Now, as well as measuring everything, you can also model everything. And we would call this mass accurate modeling. So model things with enough detail that you can predict the mass of your designs. Pretty much any 3D CAD software can do this quite accurately. and you find very little difference between what you'll model and what you measure, especially if the materials you're using are homogeneous materials, so metals like aluminium and steel and so on, they model very, very accurately. Now, the second point to keep in mind is there's a hierarchy to weight saving. So I would like to think that we break a car up into decisions that we make either at the high level conceptual, decisions around the car, the assembly level, and the part level. And the biggest weight savings are at the concept level, not at the part level. So if we're working at the part level, we can change dimensions of things. So we can make ribs thinner or thicker. We can change the material of the component. We can change the rough geometry. But the maximum amount of weight we can save is the weight of the component itself. So there's very limited weight savings to have generally when we're looking at the component level. The next level up would be the assembly level, and that's where we're choosing what components are going to be in the assembly. So here, instead of doing little details on a part, we can eliminate parts altogether. Now, if we're at the assembly level, we can have a particular look at things like how many connecting faces are there. So if you can remove a whole series of bolts and components and remove mating faces, you can save quite a lot of weight in that process. Now, a good example of that at ECU would be our WUB, and that's where we've combined the hub and the wheel center. And in doing so, we eliminated a number of parts, especially some of the large fasteners. And we end up with a lighter system, but also a more efficient, stiffer, and stronger system. So we can save more weight at the assembly level than we can at the part level, but there's one more area we can go, and that's to the whole concept level. And that's when we're starting to make big decisions about the car. For instance, if we're looking at that suspension system, at the concept level, we can say, well, maybe we do a direct acting suspension system instead of rockers. And then we can eliminate whole systems and whole parts from the whole assembly of the vehicle. Big weight savings. But it's worth noting, when we're at that conceptual level, we've got to be pretty careful because there's not an easy one-to-one relationship between decisions and performance of the vehicle. For example, if we were looking at the systems that add performance, we might go, oh, okay, it's a race car, let's add some wings to that. We've got downforce there. Absolutely, we're going to add some weight, but we're going to increase performance more than that. And then we look at, say, the engine. Add a bit of performance, adds a little bit of weight, but overall the car is faster. Then we can go, what about a DRS system? Okay, a little bit more weight, car's faster. And what about a gear shifting? A little bit more weight, car is faster. Okay, we put the driver in a low down position. Okay, it extends the car a little, but now we've got better aero to rear wing and a lower center of gravity. Overall, more performance. But we keep adding on things that are adding weight to the vehicle. And we end up with a complex system that is too heavy and overall has lower performance than if we decided to not run some of those systems. In terms of optimization, this would just be a problem with lots of variables that are interrelated. And we find that with cars, is that the variables and decisions we're making are not independent of each other. Now, if we look through the history of vehicles, we see examples where really good designers are able to cut through that noise and come up with concepts that are new, but significantly better performance. And I think a really good example is the original Mini. So that's a car where so much has been taken away from it. It's really very, very simple. It's front wheel drive, which from a dynamics point of view isn't that great. But overall, the vehicle was not only a very successful vehicle on the market, it was also successful in motorsports. So if you're going to be looking for weight savings, you need to be looking at the concept level first, rather than just jumping to individual part optimization. Now, in contrast to that, the third point is sweat the small details. Now, this seems, I think, counterintuitive to looking at the overall concept, but an overall concept can be ruined if you don't pay attention to all of the little things. because all of the little things can add up with mass very, very quickly. And anybody that has built a Formula SAE car or a Formula student car would know that the weight you get in the workshop is usually a lot less than the weight you end up with the final car ready to go at comp. All those little things that are added at the end tack on a lot of weight very quickly. We tend to ignore things like covers, or we just chuck extra bolts in without realizing it, or things like finishes, paint, and so on. They all add significant weight that if it's not accounted for, you can be quite surprised why your model on the CAD software doesn't match up with what you've got in real life. And the smallest details that I think are definitely worth tracking are fasteners. Fasteners are a really good insight into the number of components and connections you have. If you have a car with a lot of fasteners, you have a lot of connections, and connections, they weigh. In your assemblies, you try to eliminate the extra parts and try to get rid of some of those connections and make one part do the job of a couple of parts. If you're working with something like a composite tub, all of those little connections that you have where you attach something to the tub, they all weigh a reasonable amount of weight. So any weight saving that you get in one of those connections is going to be multiplied many times. So often looking at those small details, especially where you've got something repeated over and over again, which we see a lot of in suspension systems, paying a little bit of attention to those small details can gain you big rewards at the end of the project. Now, the fourth point that I think is really important is to know the loads that are going through your car. Now, you'll have seen in previous videos, I've done some suspension loading and some implications that come from suspension loading. And that suspension loading wasn't really being done to absolutely accurately get what are the suspension loads that are going through. Certainly not from a vehicle dynamics point of view. What I was doing that video for and those calculations for was to start feeding loads into sizing components. So we are, when we're sizing components, going to apply safety factors anyway. So you don't necessarily need to know the load within 3 significant figures or anything super close within 1%, because we're going to apply a fairly healthy safety factor to that. But we do want to know, are we dealing with loads that are sort of a kilonewton or loads that are 10 kilonewtons? They could be very, very different designs to resist those loads. The other thing we want to know is what direction are the loads going? So if we know the direction of loads and the load path, so how the stress is traveling through components, we can put material in our components exactly where it needs to be. So we can put it in the load path, which not just ends up with strong parts, but also really stiff parts. So we don't want parts that are deflecting and systems that are deflecting too much. And knowing where our loads are going really helps with that design work. Now, there's 2 main ways that we can approach getting better knowledge about the loads. The first that I've already mentioned is doing some calculations. Now, I appreciate that not everyone watching these videos has an engineering background, but to give it some sort of context, it's the sort of material that you're likely to learn in the first year of engineering. So it is somewhat accessible. Now, the other way that we can do the loads is by measuring. And this is not unlike when we were looking at knowing where the mass is. We either calculate or measure, and preferably we do both, because the more we measure, the more accurate we can make our calculations. Those two actually sit together. And an example of measuring loads might be to put strain gauges or load cells on suspension members. Now, this is almost less accessible than if we were to do the calculations, because the equipment involved with that can be quite pricey. And just like the calculations, there's a margin of error. When we take these measurements, especially from strain gauges, you often have a fair bit of noise in the signal, and you're only measuring what the car is doing while you're doing the measuring. So you're not measuring any events outside of that. For example, if you're taking the car around a track, you're not measuring the loads that might be apparent if you hit a curb in the parking lot. So regardless of whether you're calculating or you're doing direct measurements, you still need to apply some sort of safety factor, because even though we've improved our knowledge of the loading, we still don't have the idea of what it's going to have throughout its whole life. in all cases. So we're still going to need safety factors there. So once we have the loads, we move on to point 5, and that is know your materials, or get to know your materials better. There's a lot of materials that we use in the manufacture of a car. Generally, we can use sort of metals, so steel, aluminium, and if you're particularly excited, you might use titanium or magnesium, and composite materials. So fiberglass is fairly straightforward to use, and carbon fiber is even reasonably accessible. So there's a lot of materials we can use, especially if we start adding 3D printed materials, and some of those plastics are becoming very good now. Each material we're going to use is going to have its own strength and stiffness. And depending on the system in the car, will depend on whether we're chasing strength or stiffness, or both. Now, some materials are suitable for some components on a car, some materials aren't. And knowing all of the details of the material, including things like manufacturability, weldability, fatigue loading, all of these things come into play into choosing the right material for the particular circumstance. Now, this can be quite intimidating at first, because not only do we break materials up into their different areas, those steels, aluminiums, titaniums, composites, and so on, but within each family, there's a whole heap of different grades. So if we look at aluminium, we could have 6 series or 5 series or 7 series, and for each of those, different heat treatments involved. And so picking the right material can often feel like you're wading through too many options. Now, one of the ways that you can reduce this is just by using more materials, one by one. Each time you use a new material, you get to understand how it works. Now, when you're doing this, if you do have access to test equipment, like most universities do, and I realize this is not something that a lot of people at home have access to, you can actually start to test samples of these materials as well. So when it comes to things like composites and new 3D printing materials, we've done a lot of testing. So we've done testing of dog bone samples, we test different adhesives, we test composite panels with different skins and cores, and just about anything we can think of. So if you do have access to some of this test equipment, you really should be spending some time on it. You can learn a lot about how materials work by doing this sort of test work. Now, one thing I'm not a fan of is direct substitution of materials. So you might have a part that is, say, made out of steel, and you think, well, okay, I can replace that with titanium. And if the part has been designed well for steel, it's unlikely to be designed well for titanium. First of all, we're going to be looking at materials that have got very different densities, very different strengths, different manufacturabilities, and different weldabilities. So the replacement of titanium, if it was a fabricated part, you really need to do the work around making sure your welds are going to hold together. Likewise, in a more extreme example, would is if you were to replace a steel part with an aluminium part. So often we're working with a steel part, it might be fabricated, and then an aluminium part, we really don't want to be doing a lot of welding of thin sheet aluminium. Instead, we're going to try and machine a part. So very rarely we're going to take a part that is designed for steel and make it out of aluminium. So direct substitution of materials very rarely is going to be something that's going to help you save weight on a car. Now, one point to make at the end of this is density is not the same as mass. Just because aluminium is less dense than steel doesn't mean that an aluminium part is going to be lighter than a well-designed steel part, especially if that part has been designed for good fatigue life, where we're going to generally need a lot more aluminium and good radiuses and everything to deal with that. And following on from knowing our materials, our 6th point is to know our manufacturing processes. Combining our materials and our manufacturing processes gives us a toolbox that we can use to design parts on the car and to manufacture parts on the car. It's very rare that we're going to isolate the manufacturing processes from the material. For example, if we're working with an aluminium part, we're likely going to be doing machining. If we're working with steel fabrications, we're going to be welding. If we're working with composites, we're going to be molding. So we don't want to divorce our manufacturing from our design. If we understand our manufacturing well, it's going to give us ideas for design. And likewise, when we're designing, we want to be considering the manufacturing processes we're going to be using at the end of the project. Furthermore, the strength that we get out of our materials and of our parts is often dependent on our manufacturing processes. If we're making fabricated parts and our welding processes aren't good, they will fail at much lower loads at the welds. This is even more apparent when we start working with composites, where poor work and poor preparation in composite manufacture can lead to poor consolidation, poor skin to core adhesion, and a lot of voids in the composite part. All of these reducing strength, sometimes catastrophically reducing strength. So good knowledge of your manufacturing processes and how to get the most out of your materials is vital. It's actually one of the things that has really excited me about Formula SAE vehicles, especially as we've seen manufacturing techniques develop over the last couple of decades. As a student, I couldn't have imagined how valuable 3D printing would have been in today's time. And likewise, as we were doing our first composite cars as a student, I didn't realize how accessible that technology would be today. So just like your knowledge around materials, if you want to get better at manufacturing processes, you need to try things out. Now, I'm a big fan of trying out new techniques in a workshop, and it's pretty easy to try new manufacturing techniques on low risk items on a car. So there are plenty of cases in a car where the loads going through the parts are pretty minimal, and you can try different manufacturing techniques in order to get an understanding of the manufacturing before applying it to a more critical part. One of my favorite examples at ECU has been our CV boots. So when 3D printers weren't as common as they are now, we actually had an old Stratasys machine that was about $100,000 for a 3D printer. We decided, well, what if we tried to mold our own boots out of urethane? And this is because we were spending days going around all of the shops in Perth looking for CV boots that were small enough or could be modified, and they just weren't that suitable. In the end, we came up with a technique that was pretty quick. It took about an hour to print the molds, and then about every 15 minutes you'd have a new CV boot. And they were lighter, but not a huge impact. But the techniques that we use did have an impact in the future, and they're remarkably similar molding techniques to what's going around now in terms of forged carbon. Now, for those of you that don't know, forged carbon, it's not a great term for it. It involves taking a mold, putting in a whole bunch of chopped up carbon fiber and pouring in resin, like an epoxy resin, allowing that to set. And you can end up with parts that are very, very strong, about the strength of aluminium parts. Now, we had no idea that the techniques that we were developing for CV boots would be used in this way in the future. But by playing around with those manufacturing technologies, it gave us different design insights. The seventh and final point about lightweight isn't actually a suggestion at all. It's not an idea of how to do things. It's merely an observation that comes from being involved with trying to do extreme lightweighting for so long. And that is that making things lightweight doesn't mean that you're making them less reliable. In fact, I think the opposite might be true. The techniques I've mentioned in this video in order to gain lightweight are generally about increasing your knowledge, knowing where the weight is, knowing the loads, knowing the manufacturing, knowing the materials, looking at all of the small details. All of these things increase your knowledge of the vehicle. And as you increase the knowledge of your design and the materials and the loads that you're working with, it actually makes it easier to make parts that are more efficient. So they only have material in the paths that you're expecting it to be in order to hit the strength and stiffness targets. Now, I will say there are plenty of examples of what I would say dumb weight saving. That is just taking a component, reducing its weight without any thought of where the loads are or what sort of strength it has to do. Now, that will absolutely lead to reliability concerns, but that's not how I go about saving weight on cars. There's also, at a conceptual level, plenty of dumb ways to save weight as well. A really good example of this is in Formula SAE. When I first got started, it was really common to have a single brake on the rear differential instead of two brakes. Now, the idea here is that you can save the weight of a disc, save the weight of a caliper, and the torque will be transmitted to both sides through the LSD. But there's a couple of problems with that. One is that the torque is going to be transmitted unevenly. And generally, cars with that single disc on a limited slip diff, they either pulled one way predictably, or they were completely unpredictable in their brake application. And on top of that, in order to make a Formula SAE car turn well into a corner, you generally need a little bit more rear brake than you think you do. So for the weight of one disc and one brake caliper, you've now made your braking system significantly compromised. So I wouldn't say that that is a really good weight saving. You know, an equivalent in engine might be just going in and taking out 3 out of the 4 pistons. You've saved a little bit of weight, but you've cost yourself a lot of power. The other thing that reducing weight does is it also reduces the loads on the car. A 2-ton car roughly has double the loads on it as a 1-ton car, which has roughly double the loads as a 500-kilo car. And we see this if we look at modern cars that have got quite heavy, just how big all of the components have gotten on some of these cars. Now, this is especially relevant for when we're starting to look at ICVs, so cars that are built using some components off full-size vehicles, is that any of the components used off a full-size vehicle in a car that weighs half as much, those components are generally going to be twice as strong as they need to be. So even though those cars have got a lot lighter, the reliability of those components has increased. And the last thing that I wanted to mention about this reliability is the techniques I've mentioned for reducing weight, they're all iterative. They're about increasing knowledge, trying something out, applying the lessons from that to the next time where you try a further extension of that. And so that iterative process, as you're going through and you're doing test after test, design after design, manufacturing a vehicle after another vehicle, you start to iron out those reliability concerns. And I've seen this firsthand in the FSA vehicles that I've been involved with. Sometimes we'll add complexity trying to chase performance, but all we're doing is adding extra systems. And every system that we add adds another potential failure point. And your reliability of the overall car is like a multiplication of the reliability of every individual system. So the more systems that we add, the more complexity we add, and often the more weight we add, we're actually decreasing reliability, and sometimes considerably so. So now I want to draw it back to Project 171. When we're working in Formula SAE, generally trying to build the lightest car that we can for a given set of resources and time in a particular year. But for Project 171, my goal is not to build the lightest car possible. I have a bit of a budget for weight. I'm hoping that the car will be somewhere between 500 and 650 kilos. I think if it's any greater than 650 kilos, I'm probably going to have to build another one just to get the weight down. If I was looking to build the lightest car possible, I would have to make some changes to the concept. The 50 style or the 60 style bodywork, out it would go. I might even turf things like the roll bar. And if we're looking at motorsport, a lot of the rules in motorsport are really to stop designers from going too far. If you can get a performance advantage by reducing weight, and that's a competitive advantage, even though it costs you safety, there's plenty of examples of teams doing that in motorsport in the past. So the decisions around Project 171 are not going to be purely driven by weight savings. On the flip side of that, I don't want a heavy car. I don't like heavy cars. I think cars have got far too heavy over time. I think a light car turns better. I think it's more engaging. As you take the loads down, you can eliminate things like power steering. You can use smaller, lighter, less powerful engines. You can have a lot of fun in a small, lightweight car. So I'm keen to hear from you, especially if you think that there's something that we can learn from Formula SAE that we can apply to home-built cars, or whether it's just too separate and the lessons that we might learn in Formula SAE just might not be applicable to something that's going to be road registered. So please leave your comments on your way to liking this video, and if you haven't already, subscribing to this channel, and I thank you for your time.